Hi students, welcome to another video on control systems. So in this video we will see the problems on time responsive systems. Before we actually start with the problems, so let us go through the initial slides. Okay, this is okay. Now we will start with the problem. Okay, let me see. Okay, this is sorry. It is okay. This is the problem what we're looking at. A low inertia plotter is shown in the block diagram. Okay, this is the block diagram. Let me write the block diagram what I have. So the block diagram consists of double feedback loop. So it has got a forward transfer function of 100 by a square. It has got one negative feedback with the feedback quantity as k into s, and of course it's negative feedback. There is another negative feedback which is unity feedback. This is what we have, and this is RFS, and this is theta base. Let me write what all things we are supposed to find. So we are asked to find, oh, okay, let us hold this part A for the time being, because we have not yet discussed what is ESS, that is steady state error. So let me just put a hold on calculating the first part. So let us move to the B part, where it says select a value of k such that it results in zero overshoot for a step input, but as rapid as response as it attainable. So we are supposed to have a overshoot which is zero, and for a step input, for the R of t is equal to step input ut, and it should have a very rapid response. Okay, let us come to this now. This is the block diagram what we have. We are asked to find the value of k so that there is no overshoot, and it attains what the final state as early as possible. Now let us first find whether this system is a second order system or not, because we know that for the time being, so what we know is we know a second order system having its denominator as s square plus 2 zeta omega ns plus omega n square as the denominator, which will result in the poles at a complex position where the value of zeta is between 0 and 1. If the value of zeta is between 0 and 1, we know that this is the pole position. And for such a system, if you apply a step input, so if this is r of t is equal to magnitude 1, so we saw in the previous videos, we're going to end up with a response something like this. This will end up with some peak time, and this is going to have some overshoot. This will have some settling time, all those stuff. This is what is C of t of the system. C of t of the system, that is the response of the system. So this is CFS. Now what is asked is, so if you want to get this type of response, the value of zeta has to be between 0 and 1. So before we actually go into this problem, so let us spend some time on the time response of the system. Suppose if you take a second order system with some value of zeta, for a r of t of unit step function, this is r of t. If the value of zeta is equal to zeta 1, assume that this results in a transfer function c1 of t. So let us assume that this is what is c1 of t, and let us take another zeta which is zeta 2. Assume that let it go like this, and this is having a response of the like this. So this is going like this. So this is for a zeta 1, this is for zeta 2, and let us take another value which is zeta 3, maybe something like this. So this is what is zeta 3. So now this is zeta 3, and let us zeta 1 over zeta 2 or zeta 3. Let us take zeta 4, where zeta 4 is something like this. So it is going like this, and it's not going above that. So this is zeta 4, and this is zeta 5, somewhere here. This is zeta 5. So this is the response. So I have the response of a second order system having this as a transfer function. So CFS by RFS is given by omega n square plus so and so. For this system, if I give a unit step input, R of t is equal to U of t, this is a type of response. So this is a type of response for different values of zeta. Suppose if I try to relate the values of zeta 1, zeta 2, zeta 3, if you can see, zeta 2 is having the maximum response, maximum overshoot. So now let me write zeta 2, zeta 1, zeta 3, zeta 4, zeta 5. So these are different values of zeta. Why I am writing zeta 2 here is this is the peak one what you have. So if you can have a look at this, for first three zetas, so there is an overshoot. For the next two zeta, that is zeta 4 and zeta 5, there is no overshoot. The output is not going above the R of t, that is equal to 1. So the first three values of zeta is between 0 and 1. Is between 0 and 1. So among this, zeta 2 is the least. Zeta 2 is the least. So zeta 2 is less than zeta 1, and it is less than zeta 3. So among these three, zeta 1, zeta 2, zeta 3, zeta 2 is the least one, zeta 4 is the maximum, and of course when I say maximum, it is still less than 1, but among this it is maximum. So coming to zeta 4 and zeta 5, since there is no overshoot happening, the zeta value is greater than 1, is greater than or equal to 1. So among this zeta 4 and zeta 5, if you can see here, zeta 4 is not having a overshoot, but it is reaching the value bit sooner. It is reaching the value of 1 bit sooner compared to this zeta 5, because zeta 5 may take longer time to reach that one. So it may take too much longer time. So this is what is zeta 5 is. So now what does this zeta 4 zeta 5 is? Of course, if you want to compare now, zeta 4 is certainly less than zeta 5, but they are greater than or equal to 1. So if you can see here, for zeta equal to 1, for zeta equal to 1, if you substitute this expression for NP, what is NP you have? It is e power minus zeta pi by 1 minus zeta square. So whenever you have this zeta is equal to 1, zeta is equal to 1, so this term becomes 0. So then this term becomes 0, then you have e power minus infinity, so which is equal to 0 now. So now what do you mean by MP equal to 0? MP equal to 0 stands for no overshoot. No overshoot. Whenever you come across uh, a situation where there is no overshoot, then zeta has to be greater than or equal to 1. So this is the what understanding of that statement where there is no overshoot. If there is a overshoot, then zeta value has to be between 0 and 1. Has to be between greater than 0 and less than 1. If there is no overshoot, means zeta can be either equal to 1 or greater than 1, because there is no overshoot. So no overshoot means what? If there is a problem set, no overshoot. No overshoot in the response means then zeta is greater than or equal to 1. Then what is the exact value? Suppose if zeta is equal to 1, what does it mean? The MP is 0, but it reaches the final state sooner compared to other values of zeta. That is other values of zeta which is greater than 1. So that's why if you have no overshoot, then zeta is between 0 and 1. Now if you have no overshoot, but reaches the output as early as possible, as early as possible means then zeta is equal to, suppose if zeta is equal to 1 is there is no overshoot, but among the system response it reaches the steady state, it reaches the final state of 1, that is final state 1 sooner compared to other values of zeta which is greater than 1. So in this problem what they have said is, this they have said this, so select a value of k such that will result in a zero overshoot to a step input but as rapid response as it attainable. So this means that we have to consider the value of zeta as 1. Zeta as 1. By considering zeta as 1, we are supposed to find the value of k, or for what value of k you will get zeta is equal to 1 is the question. So now ultimately to this transfer function you are asked to find the value of k for which zeta becomes 1. So when you have a zeta to be used, you should have the closed loop transfer function. So what are the closed loop transfer function of this system? You have this as the system. Okay, let me just write it here. So you have this as the system now. So what is the system? You have a system having a transfer function. So let me write the modified transfer function. What you have is something like this. So what I have, so you can first reduce this. So can you see this reduction becomes, can it become like this? It is 100 divided by a square plus ks. So is it not the reduction of this? So it is the reduction of that. So how it came is, it's actually 100 by a square divided by 1 plus 100 by a square into ks. If you solve for this, take the LCM. Is it not 100 by a square by a square plus 100 ks by a square? This a square will go with this, so you'll end up with 100 by a square plus 100 ks. So this is ks into 100. So this is also, this is the transfer function. This is the reduction of this feedback, and then what you have this minus, and then you have this. So what is the overall transfer function? If it is r of s and theta of s, so this is actually the first inner loop feedback reduction. So finally you're going to have the transfer function which is 100 divided by s square plus 100 ks plus 100. So now this is what is CFS by RFS. CFS by, sorry, this is RFS, this is CFS. So now I have a transfer function which is corresponding to the CFS by RFS. Now let me write, this is my, so this is this word, let me just write the CD number. This is, okay, let me write it. So I have CFS by RFS is equal to 100 by a square plus 100 ks plus 100. Equate this to the standard form, omega n square by a square plus 2 zeta omega ns plus omega n square. This is the transfer function, standard transfer function, and the particular transfer function you have for the system. So now you try to equate the coefficients of s power 0. So when I equate the coefficients of equating s power 0 coefficients, so don't you have it as 100 is equal to omega n square, from which can we write omega n is equal to root of 100, which is nothing but 10 radian per second. Then what you have, 2 this is 100, then you have it is 100k is equal to 2 zeta omega n. So that's what is the coefficient of This is equating quotients of S square 1. Of course, you can see quotient of S square is 1. So first you make the quotient of S square 1 and then you start equating them. So what do you have now? So we are asked to find the value of k such that zeta is 1. So where zeta is equal to 1 given directly, it's not given directly, but it is said that no overshoot plus reaches output quickly. So it's a rapid response. It's a rapid response. Rapid response and no overshoot means that zeta is equal to 1. So it is 100k is equal to 2 into 1 into, what is this again? It is 10. So what is k? K is now 20 by 100. So this will go and you have 2 by 10, which is 0.5. So it is 2 by 10 is, sorry, this is 0.2. So if the value of k is 0.2, this system will end up with what type of response? This will end up with a response which is no overshoot and it reaches the steady state quickly. It reaches the steady state quickly. If this k is equal to 0.2, what will happen? It will reach something like this. It will reach quickly without overshoot, without any overshoot. So that's what is the meaning of this particular problem. Okay. Okay, fine. So let us go to next problem. What we have this. Okay, I'll come to this A part later. Okay, now what we have this. A control system for positioning the head of a floppy disk drive as a closed loop transfer function given by CFS by RFS is given there. Plot the pole and zeros of the system and discuss the dominance of complex pole. What overshoot for a step input do you expect? Okay, let us write the transfer function whatever you have. Let me write the transfer function I have there. So what the transfer function you have? You have CFS by RFS. CFS by RFS is equal to 0.313 S plus 0.8 divided by S plus 0.25 and S square plus 0.3 plus 1 is 0.3 S plus 1. Okay. And okay, dominance. Okay, let us see what is this. We are asked to plot the pole zeros. So we know that 0 is at minus 0.8. Poles are at minus 0.25, and this is, let us see what are the roots of it. So it is 1, and then it is second degree. A is 1, B is 0.3, and C is 1. Let me find the roots. So roots are minus 0.15 plus or minus j. It's a complex one. It is 0.988. So where are the poles and zeros? So on the S plane, if you write where are the poles now? So 0 is at minus 0.8, pole is at minus 0.25. So on the real axis, the other two poles are, it is minus 0.15 and here it is plus j 0.98. This is minus j 0.988. The reference, this is okay. Now you have, sorry, this because your real part is this, so you have the poles. Correct. We have poles here, here, and here, and you have a 0 here. So now we actually have totally three poles, and 1 0. So if you look at these poles, the question is, out of these three poles, which is the dominant pole? the pole which has a lesser real part value happens to be the dominant pole. That is, poles which are closer to this imagined axis. So this is my imagined axis. The poles which are closer to the imagined axis are the dominant pole. In this case, this is the real part of the complex poles, and this is the real part of one of the pole. So this is the dominant pole. So this is called as dominant poles, meaning s square plus 0.3 s plus 1 is the system transfer function which is representing the dominant poles, What it says next, it asks for, okay, what overshoot of a step input do you expect? Now, even though the system has three poles, the response of the system is dominated by this particular poles. So these two poles. Now, if you want to find what is the response, now you have a system having this type of transfer function. If you apply input of r of t is equal to 1, you will certainly have a response something like this, which is governed by majorly this term. So it is as well as considering a term which is something like 1 over s square plus 0.3 s plus 1, rather than considering all other terms. So now, even though you have a 0, even though you have some magnitude, let us not worry about that. Even though you have a pole here, let us not worry about that. The response is now dominated by this particular dominant pole, which is closer to the imagined axis. Now you take this equation and equate to s square plus 2 zeta omega ns plus omega n square. Now in this, find out what is omega n. So omega n square is 1, so omega n is also 1 radian per second. 2 zeta omega n is 0.3. Then find out what is zeta. So what is zeta is equal to, it is 0.3 by 2 into 1. So it is 0.3 by 2, so zeta is equal to 0.15. So zeta is equal to 0.15 is the system damping factor, If a system has a damping factor of zeta is equal to 0.15, then what is the overshoot for a step input? We know that overshoot is given by e power minus zeta pi by root of 1 minus zeta square. So you substitute onto this and try to find out what is MP for a step input. Let me do that. So it is now shift e power minus, so open the parenthesis, it is 0.15 into pi divided by, open the parenthesis, open the square root, again open 1 minus 0.15 square, close equals. So it is 0.62 is the value of input. So overshoot is 0.62, meaning if you apply step input of magnitude 1, if this is t and if this is r of t, your c of t will have a response something like this. So it will just have an overshoot almost up to 62%. 62% will be the overshoot. It's nothing but from 1 it will go up to 62% above that. So this magnitude at c t is equal to tp. At peak time, this will become 1.62. 1.62. So this is the overshoot is 62%. The corresponding value of the response at t is equal to peak time. This is your TP. This is TP. This is from 0. So at TP, you're going to have a magnitude of 1.62, which is 62% more than the desired value. So now the answer for this is this is the dominant pole. The pole 0 positions are listed here or pasted here, and you have a zeta of 0.15, and it is going to have an overshoot of 62%. We should move to next problem. What does next problem says? So that's what what overshoot a step input do you expect is I'm expecting 62% overshoot. Okay, this is another problem. So you have a system with negative feedback, negative unity feedback. You have GFS is given by K by so and so. You're asked to find the overshoot and the settling time for a step input, and what is the range of K so that settling time is less than 1 second. So now what is this? You have feedback system whose transfer function, whose GFS is given by S into S plus root of OK, and you have the unity feedback minus what is that you are asked to find? You are asked to find MP and TS of 2%, and what is the value of K so that it is TS is TS is TS is 1 second. Okay, let me just show you what are things we are asked to find. We are asked to find this for R of t is equal to a unit step input. So we know this. What is CFS by RFS of this? CFS by RFS of this is K by S square plus S into root of 2K plus K. This is what is this. So equating this to denominator, of course it's only necessary to equate the denominator. Even if the numerator is not tallying with omega n square, you are not supposed to worry. A square plus 2 zeta omega ns plus omega n square. Even though this is, of course in this case it is tallying, even though this is not tallying, we're not supposed to worry, because the response depends on the pole position. Whether you have a 0 or not, it doesn't matter in terms of the shape. The magnitude may slightly differ. So since we are looking at the overshoot and all those things, it will not change. So now what we have, so equating the coefficients of s power 0, you have omega n square is equal to k, so that omega n becomes a root of k, and you have 2 zeta omega n is equal to a root of 2k. What is asked to find? You are asked to find MP and so on. So for which you should know the value of zeta. So from this, can I write zeta is equal to under root of 2k by 2 into omega n. So it is now under root of 2k. What is omega n? Omega n is the root of k. So this k and this k will go off. So this is actually a root of 2, and this is root 2 root 2. There are two roots. So this is 1 over root 2. So 1 over root 2 is, so now it is the root of 2, 1 over that is 0.707. So it is 0.707. This is the value of zeta. If you know zeta, you know how to find MP. So what is MP now? MP is given by e power minus zeta pi by 1 minus zeta square the root. How much is this now? So this is, so now this becomes okay, let me just find out. It is shift minus of zeta is 0.707 into pi divided by under root of 1 minus, sorry, 1 minus 0.707 square, it is square, this is square, plus can you see it is into 0.043, which is nothing but 4.32% overshoot. It is hardly a very small overshoot. It is 4.3%. Then what is TS? TS is equal to, for 2%, we know that it is 4 by zeta omega. So it is 4 by zeta omega n, which happens to be 4 by zeta is 0.707, omega n is root of k. Omega n is root of k. So then how much is this? So it is 4 divided by 0.707. Can you see it is now 5.65 by root k? This is what is TS. This is what is TS. Of course, depending on the value of k, the TS will change. So this is what is the TS value. Then what is asked? What is the second part of it? You are asked to find the value of k if the TS has to be 1 second. So now there is a second condition. What does the second condition say? What is the value of k so that the settling time is 2% settling time is 1 second. So it is 57. Let us find that. So what is that you are supposed to find is the value of k. So let me write that. TS is equal to, because you are asked to find for 2%, it is 4 by zeta omega n. Now this is equal to 1 second is equal to 4, okay, 0.707 root of k, correct? So this is what you have. So this is nothing but 1 is equal to, how much is that? 5.65 by root of k. So that now k is equal to 5.65 whole square. That is square of that means 32. If k is equal to 32, so if the value of k is greater than 32, then the value of TS is less than 1 second. This is how you can able to do. This is 3 point. So this is how we could able to find the values for the given problem. Okay, so we will in the next video we'll try to learn what is this steady state error and various steady state error coefficient depending on the type of input you are giving. So you can have three different inputs, which can be a step input, ramp input, or it can be a parabolic input. We'll just see those things in the next video.